So we are in part 3, the matter power spectrum, which, as we said yesterday, can be decomposed in the square of a transfer function for non-relativistic matter times the primordial spectrum. The primordial spectrum gets an amplitude and a tilt. The curly P of curvature has a tilt dependence in ns minus 1. So ns equal 1 corresponds to a scale invariant spectrum. But because of the difference between curly P and capital P, you have a minus 4 here. Okay? We are computing now the transfer function qualitatively in the limiting case where baryons are negligible with respect to cold dark matter. And then everything follows from this master equation for delta CDM. And we gave the behavior of the solutions yesterday in the main regime. So we start from some initial conditions. Outside the Hubble radius, delta M is normalized to the curvature perturbation. So it's essentially I get a 1 here. It's not exactly 1 because there is a number of order 1 that you can compute. There is a coefficient between the curvature perturbation R and the metric perturbations phi m psi and delta CDM. So it's a number of order 1 with a bit of computation. You would see, I think it's 2 over 5 or something like this. At equality, but outside the Hubble radius, there is a small jump, but immediately after, the solution is again constant. So there is again a number of order 1 here. However, when a mode crosses the Hubble radius during radiation domination, this is before this line, there is a slow growth of the perturbation. It's like a log of k, okay? Log of k eta. While during matter domination between this line and this line, the growth is much more efficient because it's just a clustering of a self-gravitating body. And the growth goes like eta squared. So if we are a bit more specific, take a mode that enters into the Hubble radius during matter domination. Then it remains essentially equal to 1 until the line of Hubble crossing, and then it grows like eta squared. So if I normalize correctly the solution, for those modes I will find a k square eta square. I omit numerical factors. So again, why? The eta square here is just because inside the Hubble radius, perturbation grow like eta square. The k square is because you have to normalize such that on this line you get 1. Hubble crossing reads k equal to AH or k eta equal to 1. It is the same. Just replace A by a power law of eta and you will say that apart from a numerical factor, the two conditions are equivalent. So this solution is the correct one because it is still 1 on the line of Hubble crossing, and then it grows like eta square. The solution here grows like eta square, starting from this value. So I should write it as E that eta square over eta of equality squared times the value along this line, which is a log of k eta equality. So here I have k eta equality, and then it grows like eta square. Okay? So these are the solutions, very easy. And then during lambda domination, there is a slow dumping, slow reduction of the growth rate of matter. Why? We gave the reason. We said that during matter domination, phi is a constant. Phi m psi are constants. Anytime the equation of state of the universe, the total one, is changing, these quantities decay. This is why there is a small jump at equality. But now, during all this stage of lambda domination, the equation of state of the universe is going from 0 to minus 1. And during this transition, phi m psi decay. And if you use the Poisson equation, it means that delta CDM grows more slowly than these solutions. So with this, we can already give the shape of the matter power spectrum. And this is something that Shirley Ho will really need for her course. So let's draw the quantity P of, I could write as a function of proper time or conformal time. Here it's conformal time, and K at different stages. First, we will grow P. We will show P of K at initial time. So first, what does it mean initial time? We don't need to specify. We just mean some time when all perturbations are outside the Hubble radius. We don't need to say more than this, since everything is constant outside the Hubble radius. Of course, we cannot observe P of K at initial time. This is just a starting point, and then we will move with time. So at initial time, you get a power law. It's written here. It's K of ns minus 4. Okay? I will take, for simplicity, the case ns equal to 1, since we know from inflation and mainly from observation that we are very close to this case. So then it's a K to the minus 3. Okay, now we move to matter radiation equality. We started from this power spectrum, and the characteristic scale here will be the scale crossing the Hubble radius at the time of equality. It is exactly this scale here. Okay, so for scales smaller than this case, there has been no evolution of the transfer function. For the other scales, there is an enhancement due to this factor. So it's a small enhancement with this shape. So here, the solution is a K to the minus 3. And here, if I take the square of the transfer function, it's a K to the minus 3 times this amount of growth, which is a log of K squared. Squared because the transfer function is squared. So this accounts for the small growth of perturbations inside the Hubble radius during radiation domination. Okay? And next, what happens if I follow my perturbations until sometime during matter domination? So let's go up to the time of matter lambda equality. I started from this shape in K to the minus 3. I still have an important characteristic scale, which is K equality. Another characteristic scale is this one. I'm now at this time of equality. This scale is K lambda. It is a scale entering into the Hubble radius at the time of matter lambda equality. So, below this scale, there has been no evolution of the transfer function. Above this scale, we have the solution. It's a K square eta square. So along this line, it will be K square times this time square. So it grows like K square multiplied by K to the minus 3. Sorry, this is for the transfer function. Okay? So the square of the transfer function has a K to the 4. K to the 4, and I started from K to the minus 3. It gives me K to the 1. And this gives me the amount of growth of fluctuations in this triangle here, inside the Hubble radius and during matter domination. And it's a K here to the 1. Again, I start from K to the minus 3, and I multiply by the square of this, so I get this linear dependence. let's look now at those modes which entered before the time of equality. In the matter-dominated regime, they all grew by the same amount, which is equal to n squared divided by n equality squared. They spend the same time inside this region. So this is the amount of growth here during matter domination. And then again, I had a small amount of growth in this triangle that we can report from here. So the red is the amount of growth during matter domination, and the yellow during radiation domination. And as we said, the shape is the same. It's a k to the minus 3 log of k to the square. Okay, and now if we look today, the shape is essentially the same. The only thing which happened between here and here is that the growth rate was reduced. However, it's reduced by the same number for all scales. Here, the reduction of growth is scale independent during lambda domination. So it just affects the global normalization. But what we wrote before is the same, except that perturbation started to grow above just the scale which enters into the horizon today. And this is AH. So here we have AH. Here we still have K equality. We have here this behavior in K, and here in K minus 3 log K squared, with a smooth transition here. Can we see this power spectrum today? The biggest scale we could see would be the radius of our observable universe. And in fact, even this scale cannot probe the matter power spectrum, because if we want to see our full observable universe, or nearly full, we need to look at CMB anisotropies. When we map galaxies, we see only a fraction of our full observable universe. It means that we can hardly approach this scale. K equal AH, the scale crossing the Hubble radius today, gives an estimate of the size of the observable universe. So we cannot see leftward of something like here. So when people map the matter power spectrum, they see a window which is something like this one. And they probe the rise in K and the decrease in K to the minus 3 log of K squared. So when you see results from galaxy redshift survey, you see a curve looking like this. This not only is not observable, but here the results depend on the gauge in which we would make the calculation. In some other gauge, I would have a different behavior here. Okay, this is everything, provided that we neglect baryons. But now, we are going to take into account the fact that this matter power spectrum builds up from the contribution of CDM and baryons. So, case with sizable omega b. What is different from omega b? Essentially, it's a fact that baryons remain coupled to photons until the time of photon decoupling. And only after they behave as free-falling particles and can have gravitational clustering. A little subtlety is that baryons behave like free-falling particles after a time which is not exactly photon decoupling. It's after another time called the baryon drag time. Why? If you think of the visibility function g of eta, we said that this visibility function of photons has a peak at a time that we define to be photon decoupling. Decoupling is defined as a maximum of this peak. So what does this time mean? It means that it is a peak probability time at which photon last scattered. The last scattering of a given photon that we see has a maximum chance to be located at the time of decoupling. When we are in this tail here, it means that only a minority of photons still experience Thomson scattering. But you know that in our universe, there are many more photons than baryons. You saw that this has dramatic consequences in the study of Big Bang nucleosynthesis and deuterium formation, or also when you compute the temperature of recombination. It means also that here, even if you have very few photons still scattering, it's enough to keep the baryons attached to the photon fluid. And the baryons will really start to be freely falling to feel gravity more than Thomson scattering after a later time called the baryon drag time. So this is sometime after decoupling, baryon drag. It's when baryons are really released from the photon baryon fluid. And what controls this time is the relative abundance of baryons with respect to photons. So since photons have a fixed density, omega b is a parameter controlling exactly this time. So before this time, I still have this relation delta b equals 3 over 4 delta gamma that follows from thermal equilibrium with the photons. While after that time, baryons are in free fall, just like the cold dark matter particles. So what happens is that they fall in the same gravitational potential well, they equilibrate gravitationally, and so the baryons will tend to the same solution as cold dark matter. The effect on this on the matter power spectrum is not difficult to guess. Let us plot the matter power spectrum, now taking into account our two components, before the time of Hubble drag, just before the time of Hubble drag. So this is k to the minus 3. And now, if I plot the contribution from CDM to the matter power spectrum, we already drew it somewhere around here. There is a raise and then a logarithmic slope. So this is a contribution, so it is k to the minus 3 delta CDM squared. It is a contribution from the cold dark matter part, and it is the same as here. Okay. If I draw qualitatively the clustering of the baryons at that time, the baryons experienced acoustic oscillations together with the photons, and moreover, around the time of recombination and after that time, there is a considerable impact of diffusion damping. Okay? So these fluctuations are very suppressed, and the baryon part has this oscillation, which are very suppressed. So this is k to the minus 3 coming from this primordial spectrum times delta b squared. I got a question yesterday about silk damping. So when Joe Silk worked on damping, what he had in mind at the beginning was that for baryons and not for photons. So it was precisely this shape. But now we also call silk damping the effect of diffusion damping on the photons, on the CMB. Okay, so what if I make the same plot soon after baryon drag? So this was for eta before baryon drag. And now for eta, let's say it's baryon drag minus epsilon and eta equal baryon drag plus epsilon. You can simply get the result by doing a matching between the two. because you know that they are going to reach the same solution very quickly. So what you get is simply a weighted average between these two contributions. And qualitatively, it will look like the CDM part a bit reduced and with oscillations. Okay. Total P of K. So the impact of baryons on the matter power spectrum with respect to what we just said before is both a reduction of the slope, and some additional acoustic oscillations, which result from the acoustic oscillation of the photons. Okay. And these are called the baryon acoustic oscillations. And in the notes, I copied a graph. Okay, so these are numerical results that you can get from COMB or class with different baryon fractions. The first one is like infinitely small, so the baryons behave just like test particle. The second one is like more realistic, like in our universe. You see the difference is in the amplitude of the small scales, the slope on intermediate scales, and the baryon acoustic oscillation that are visible only when the baryons are significant. And Shirley-Ho will insist a lot on the use of this baryon acoustic oscillation. So the key point is that the wavelengths of this oscillation can be used as a standard ruler in the universe. But this we are not going to develop, it's for her. Okay, so if we do like for the CMB, we summarize the parameter effects. Instead of our C1 to C8, we will have P1 to P5. Okay, so parameter effects. So again, our parameter for minimal lambda CDM are AS, NS, omega B, omega matter, big omega lambda, and tau rho. The shape of the matter power spectrum is controlled by 4 quantities. The first one is a quantity giving the maximum here. So the position of the maximum depends on what? It is fixed by K equality, the scale entering the Hubble radius at equality. So the maximum depends on K equality. So it depends on the redshift of equality, or the scale factor at equality. And this is controlled, as we said yesterday, by omega m. Omega m is the parameter fixing the time of equality. The effect P2 is the shape of the power spectrum for K bigger than K equality. So when we are in this region here, the shape depends of the spectrum. Its slope depends a lot on how many baryons we had with respect to cold dark matter. Okay? It tells you in the weighted average if you are closer to the baryons or to CDM. In a model with many more baryons than CDM, there would be a dramatic reduction of the power spectrum and huge oscillations here. So the shape for K larger than K equality is controlled by omega baryons. What matters, if we want to be precise, is the relative weight here of baryons and dark matter. So what matters here is the ratio omega B over omega CDM. Okay? In terms of this parameter basis, you can just write it like this. P3 is the phase, or if you want, the location, the characteristic wave number of the baryon acoustic oscillations. So since the baryon acoustic oscillation come from the same phenomenon as the oscillation in the CMB, I repeat that in real space you would see only one feature, and these multiple peaks in Fourier space are just regularly spaced because they are the harmonics of the single feature in real space. So this phase and location of the BAO in Fourier space depends on the sound horizon. As we said, it is a sound horizon which controls the position of the oscillation in Fourier space. For the CMB, we had to divide by an angular diameter distance because the CMB spectrum was expressed in multiple space. Here we are in Fourier space. We don't need to divide by anything. This sound horizon should be computed at the baryon drag time. The baryon drag time depends very much on omega b. So this is very much dependent on omega b. Fortunately, we see omega b very well. We can measure it very well with the CMB. So we can fix omega b in advance and then really consider this scale as known when we use it as a standard ruler. Now, a small remark. Not very precise courses, people will tell you that the location of this peak is the same as the location of the CMB peak if you go back to Fourier space. So it's not true for two reasons. First, because the sound horizon at baryon drag is not the same as the sound horizon at decoupling. It's a bit larger because there has been a small increase in the sound horizon between decoupling and baryon drag. So this means that there is an intrinsic shift between the location of CMB and BAO peaks. But there is a second reason. And this maybe you don't know, even if you have done some cosmology, some of you. The second reason is that when you do the matching, okay, you have seen matching procedures in physics, it's very common. You impose, when you go from here to here, you impose continuity of the derivative. So the result of the matching depends on delta CDM before, delta B before, as well as the time derivative of delta CDM before and the time derivative of delta B before. When you do the matching, you realize that the velocity of the baryons here, which is related to the time derivative of delta B, is very important. And so actually the phase of these peaks is not the same as the phase of the peaks in delta B, but it's almost shifted by pi over 2 because it's more the velocity here which is important. So the BAO peaks are shifted with respect to the CMB peaks, both by a factor pi over 2 coming from the matching and by the difference between eta decoupling and eta at baryon drag. This is a technical detail. Okay. This was effect P3. Now P4. It's a global amplitude of the spectrum. So of course it depends on AS. This is outrageously trivial. AS was from the beginning in the matter power spectrum. It also depends on omega lambda, because when you change omega lambda, you change the duration of the lambda-dominated stage and the amount of reduction of the growth rate. If omega lambda is larger, this stage is longer, and the amplitude of the spectrum is reduced accordingly. And P5, of course, the global tilt of the spectrum is related to NS. I don't show you computer images as yesterday because this is rather trivial. You have already, the most important effect is one of omega b, and you saw it here. So let's try to recap what we can learn from the matter-power spectrum. So we have these 6 parameters. You see that tau ionization is completely irrelevant for structure formation. It's a thermodynamical effect for the photons. So it seems that we are left with 5 parameters and 5 effects. Sounds good, but this is too naive. In fact, AS and omega lambda are completely degenerate. If you map the power spectrum at a given time, they are completely degenerate. Moreover, with current experiments, the best reconstruction we have on the matter-power spectrum is from galaxy redshift surveys. And Shirley will show you that this gives P of k up to an unknown normalization factor called the light-to-mass bias. So it means that we don't measure, currently we don't measure accurately the global amplitude of the spectrum. So, in fact, we have 3 relevant parameters and 4 effects. Sounds even better. But some of these effects are very difficult to see. For instance, we don't have good data probing the turnover here. We can start to marginally see the turnover, but with large error bars. So we cannot measure K equality with accuracy. So globally, the power spectrum is able to measure these 3 parameters, but not with fantastic error bars, not as well as the CMB. But it's complementary to the CMB. For the degeneracies between parameters that you get from the matter-power spectrum are not the same as with the CMB. So it's nice to complement CMB observation with matter-power spectrum observation. In the future, the situation will be a bit more bright, even significantly better, because with very ambitious programs like LSST in the US or Euclid in Europe, but these are on long term, we will be able to map such a large region of the universe that from the data we will extract the matter-power spectrum at different times, corresponding to different redshift shells in our data. If we have the matter-power spectrum at different times, we can probe the time evolution of the transfer function, and we can probe this reduction of the growth rate. So in the future, having this time dependence, we can test the lambda CDM paradigm, see if we need to change for a dynamical dark energy model. Moreover, here we neglected the effect of neutrino mass, but the effect of neutrino mass is to make this growth rate scale dependent, and this can be tested if we have the matter-power spectrum at different times. Okay, so I'm done with the matter-power spectrum. You will learn more next week. We will end up with very short parts, which are like some examples of how you can apply all this knowledge to your field if you are particle physicists. So we will recap the effect of dark matter on the CMB and power spectrum, as well as the effect of dark energy. We will not cover all possibilities. I just want to give you a flavor of what can be learned. And then probably we will have 10 minutes left in order to say something about polarization and tensors, because now it's going to be simple and we will go fast. So, effect, dark matter effects. Okay, first, you know that most of the dark matter in the universe seems to be cold. Going back in time, in the 80s, there was a strong competition between 2 models, cold and hot dark matter. Cold dark matter is defined as matter with a negligible velocity dispersion. And usually this comes from the fact that it decoupled when the particles were already strongly non-relativistic. So you have, this is a case of the WIMS paradigm, also of the axion, although the decoupling is completely different. Maybe there is no decoupling. These are cold dark matter candidates. Hot dark matter candidates are particles with a large velocity dispersion. This is the case, for instance, of massive neutrinos because they decouple when they are still relativistic. And so if you have a mass of the order of the EV, then the neutrino velocity dispersion today is just a fraction of the speed of light. It's 10 or 100 times smaller, but it's still very fast. Okay. In a hot dark matter scenario, you probably know that the matter power spectrum would be dramatically different. So we have seen that for cold dark matter, it looks something like this. If you make computation in a hot dark matter scenario, there is a dramatic reduction of power here. The slope is completely different. In the 80s, the two were open possibilities, but very early, even with very rough large-scale structure data, it became clear in the early 90s that this was not compatible with the clustering of galaxies. Still, we could have essentially cold dark matter and a little fraction of hot dark matter. And in fact, this is what we expect from the observations that neutrinos have a mass. Okay. So we will not discuss the effect of these massive neutrinos today because it will also be discussed next week. So we focus on the dominant dark matter, the effect of the dominant dark matter part. So lambda CDM assumes pure cold dark matter and deviations from this scenario which are investigated include the possibility that dark matter would be warm. It means that it would have some intermediate value of the velocity dispersion. This could be the case if dark matter was made, for instance, of sterile neutrinos with a key EV mass. In this case, you see such a reduction, but pushed to smaller scales because the velocity dispersion is much smaller than for active neutrinos. And so it's difficult to exclude unless you have very good data on very small scales. But very small scales are very nonlinear. So this is one possibility. You could have some weakly coupled dark matter. Instead of assuming that it's completely decoupled, you put some non-standard interaction. You could have some self-interacting dark matter. There are many possibilities, and in principle, most of them can be tested with the CMB and matter power spectrum. Let us stick now to ordinary cold dark matter. The only parameter we can measure for cold dark matter is omega CDM. This is what makes it very boring for a cosmologist. There is only one number in this model. So, from the CMB, it should be clear now for you that we can measure omega CDM. Because in the effect C2 of yesterday, the ratio of odd to even peaks, we have a way to measure omega B very accurately. And from the amplitude of all peaks, we can measure very well omega M. This is C3, because it gives us a measurement of the time of equality. And the difference between the two is omega CDM. Omega M was also entering in the angular diameter distance relation, in the effect C1 and C4, position of the peak and of the damping envelope. But then there is some additional effect from omega lambda, so there are not very good ways to measure these two. But with this, you get a very accurate estimate of omega CDM, which, as you probably know, is measured to be close to 0.11. So the CMB probes the cold dark matter amplitude indirectly. It's not a direct effect of omega CDM. Omega CDM appears like a missing energy that you need to introduce in order to explain the CMB. And in particular, in order to obtain the right time of equality. You could say, that's good, but couldn't I have also in the CMB, couldn't I isolate a direct effect of cold dark matter perturbations? In principle, you could for the following reason. We said here that when the photons modes enter into the Hubble radius, they start to oscillate. And we said that at the beginning, there are some gravitational driving effects coming from the region where you cross the sound horizon. So if there is gravitational driving here, CDM are inhomogeneous, so they should produce a gravitational force that could impact the evolution of the photons. So in principle, there could be also a direct effect of cold dark matter. It turns out not to be the case for the reason that I said is explained in the Weinberg's book, that when you scrutinize the solution in this regime, you can show, although it's very non-trivial, that there is no gravitational back reaction of cold dark matter on photons in this regime. So I refer you to the book. It's in the discussion of the so-called Metzaros equation, if you are specifically interested in this. And also you can send me a mail. I will tell you which page it is. So there is no direct effect. It's just this indirect effect. Next, what do you gain if you use the matter power spectrum? Well, if you use P of k, you have effect P2. P2 is related to the ratio of omega B over omega CDM. Okay? So P2 is the shape of the matter power spectrum on the BAO scale, more or less. It's not a very precise measurement, but it's a consistency check of what you get with the CMB. And it works with current data. Can you see something more about cold dark matter? There is maybe a chance that you can. Because cold dark matter, even in the most popular model, can still annihilate until today. And there is a small chance that we could detect the effect of cold dark matter annihilation on the CMB. It depends very much on the cross-section of cold dark matter. So this is a field which has been investigated rather recently. So probing CDM annihilation with the CMB. When you study recombination, you have an equation of evolution for the free electron fraction. I don't write it explicitly, but in the simplest limit, it comes from a Boltzmann equation similar to the one for deuterium formation. Suppose that cold dark matter annihilates. Depending on the model, it could annihilate dominantly in different decay channels. At the end, you will always end up with extra photons, okay? Extra photons coming from this annihilation. And these photons can ionize the hydrogen atoms in the intergalactic medium. And so the effect is a bit like the one of reionization from stars. So if you want to include this effect, you have to add an extra source term where the most interesting part for you reads like the square of rho cold dark matter, the homogeneous one, times a function f of z, I will say what it is, times the average sigma v, so the thermal cross-section, divided by the mass of the particle. This is the fraction of the energy produced by the annihilation released say, absorbed by hydrogen. So depending in which decay channel your cold dark matter will annihilate, annihilation channel, this fraction will be bigger or smaller, and it will be usually time dependent. So if, in order to compute f of z, you have to do a little bit of, been studied for many models, in particular by the group of Fink-Biner. Okay, so there are recent references on this topic. So the effect.
Why is it divided by less, not less square?
Yes, you must be right. Okay. You must be right. There must be a square. I'm not. You see here my limitations in particle physics. So you are probably right. You can check it in the papers. Okay. You say because it's a two-body interaction.
Well, I remember the papers.
Yeah.
But I'm just
Yeah. It's a two-body interaction. It should be a square, probably. Yeah. Okay, to be checked. Okay, if we plot the ionization fraction, in absence of this effect, it would start from 1, decay at photon decoupling, and grow again at recombination, at reionization. And we know that it grows up to 1 because of something called the Gunn-Peterson effect in quasars. So we know that the universe is fully reionized at low redshift. Because of this term, this will decrease more slowly and will reach a higher plateau, typically. And moreover, if you take into account the effect of nonlinear structure formation, you see that when the dark matter halos form, there is a large concentration of dark matter in the halos. So the term rho square coming from the homogeneous cosmological background is overseeded by the local high values of rho square in halos. And so there is this effect is like boosted at the time of halo formation, and it could contribute to the reionization. There are even some papers by Dan Hooper and other people suggesting that all the reionization could be explained with this phenomena, even if the stars were not forming. This will leave an impact in the CMB. From the course now you can have an idea of what it will do. It will shift a bit the time of recombination. So it will shift the scale of the peaks. And it will affect the effective value of tau of reionization, so it will also affect the amplitude of the peaks. People have shown that it's very difficult with the CMB to do a detailed mapping of this function as a function of time, but it seems that the CMB is mostly sensitive to the product f of z sigma v divided by m, so probably m square, evaluated around the redshift 600. This is when you are more sensitive to this effect. So it's slightly after recombination. And in order to get a sizable effect, it's nice that you don't need crazy value of sigma v, but values which are comparable to ordinary WIM scenarios. So this was used as an argument. At some point, there were some claims that gamma ray data from the Fermi satellite were pointing at a slightly unusual dark matter candidate. But this dark matter candidate would have a too large cross-section and would have been anyway ruled out by this argument. So it's good to know that this exists and that we have a small chance to measure it one day. So what else can we learn on dark matter with cosmological perturbation? So as I said, we can learn about the neutrino mass, but this is for next week. We can learn about the fact that dark matter is cold or warm, but this is an effect mainly in the P of k on very small nonlinear scales, so it's very difficult to probe, but people are trying. We could check that there is no significant coupling between cold dark matter and photons. The CMB can be used to put the best limits on such a possible coupling. If dark matter would not be annihilating but decaying, then its decay product could rayonize the hydrogen, and you could have something qualitatively similar to this. So there are many things that you could try to probe beyond the minimal CDM paradigm. Okay? This was dark matter. Now let's do the same for dark energy. So, effects, yes?
So when we were talking about the effects of this
Yes.
ionization and also the combination.
Yes.
So, but for instance, having non-instantaneous reionization, we have the same effect that let's say your reionization doesn't drop, right? Xc doesn't drop instantaneously.
Yes.
At some slope. But then is there any way of
Yeah, in order to know if the universe is rayonized by stars or by dark matter, we have so few constraints on star formation that it sounds, from the CMB alone, it sounds impossible. I can always cook up a model of star formation that will be equivalent to a model of CDM annihilation. So the only way would be to understand better star formation with other means. So for instance, in the future, there will be some data from a technique called the 21 centimeter. It's the observation of 21 centimeter emission from hydrogen at high redshift in the radio frequencies. This will allow us to better understand the thermal evolution of the universe at redshift between 5 and 10. We can have better observation of well, it's very difficult to see anything in the universe at the redshift of star formation, except with this 21 centimeter. So I think this new technique that is being developed now will be the best way to discriminate, but it will be hard. So it's better to try to see the effect here. The fact that annihilating dark matter delays recombination, and that the residual ionization fraction is higher, because these effects are not completely degenerate with those of rayonization. They affect larger values of L in the CMB. So this is more promising. Okay. So about dark energy, I don't have so much to say, because the really rich field is concerning dark energy is a study of the evolution of the matter power spectrum that will be probed with weak lengthening experiment, and this you will see next week. But concerning the CMB, what can we say? Effects of dark matter on, so mainly on the CMB, of dark energy. And I will say a bit about P of O. Okay, in the lambda CDM model, there is only one parameter accounting for the acceleration of the universe, this lambda or omega lambda. We have seen already how we can measure omega lambda, mainly from the effect, for instance, the effect C1 in the CMB, the position of the peak. Usually omega M and omega B are fixed with effect C2 and C3. So we know the sound horizon at decoupling. And omega lambda is inferred then from the angular diameter distance. And this works very well, unless you assume that the universe could be open or closed, in which case there is another degree of freedom in the angular diameter distance, and it ruins your measurement of omega lambda. Beyond omega lambda, what can we assume? We can assume, of course, that dark energy would be dynamical, okay, with an equation of state P equal W rho. Okay, this equation of state could even be time dependent. This is only a modification of the background. When people investigate models that they call WCDM or WACDM, if they consider the derivative of W, they make usually the implicit assumption that the sound speed of dark energy, delta PE, delta P dark energy over delta rho dark energy, is 1. Why? The most natural assumption for the sound speed is that the sound speed would be equal to the equation of state parameter, because this is imposed in the case of a perfect fluid. In a perfect fluid, in each point, you have an equilibrium relation P equal W rho. Take the average of this, and you will get that it is true at the level of the background. Take the difference between these two equations, and you see that it is also true at the level of perturbations. This is for a perfect fluid. Dark energy can certainly not be a perfect fluid because it has a W close to -1. If the sound speed was also close to -1 or just negative, there would be an exponential instability of the perturbations. They would grow exponentially inside the Hubble radius. Then what is the most natural value for CS square? We don't know, we don't have a model. But for scalar fields, you can show that it is equal to 1. And so people usually refer to this case and take a sound speed squared equal to 1. Keep in mind, if you work on these topics, that the sound speed of a species is a gauge-dependent quantity. With a gauge transformation, you will find a different value. So usually when people refer to the sound speed of dark energy, what they mean, even without saying it, is that they define it in the gauge co-moving with dark energy. So you can always find a gauge in which the velocity divergence, theta dark energy, is equal to 0. It means that your frame is moving together with dark energy. It is in this frame that it makes sense to define the sound speed of a given species. So the sound speed of a scalar field is equal to 1 only if you go to the gauge in which theta of the sound field, scalar field, is equal to 1. Okay. These are modifications only of the background. But since we have so little knowledge about what dark energy could be, we could try to model it with more complicated assumptions concerning the perturbations. For instance, the sound speed could be taken as a free parameter. That you would vary between 0 and 1. It cannot be 0, it can be 1. So I denote it in this way. You could assume something more complicated. You could assume that dark energy has some shear. Sigma dark energy different from 0. From what we said, it would imply that phi is different from psi in our universe. Usually, there are no good theoretical motivations behind these models. It's just a phenomenological approach. Let's try to guess from the data what dark energy could be. Now, what are the consequences on the spectra? You should distinguish between two cases. First, if CS squared is not very small. Very small. What I mean by very small would be, for instance, 10 to the minus 1, 10 to the minus 2, 10 to the minus 3. If this is not the case, then the perturbation of dark energy will never grow significantly. This is related to what is called the Jeans instability. It appears in many sectors of cosmology. Varying CS square means varying the pressure perturbations in your fluid. A large CS square means large pressure in the fluid that will resist to gravitational compression. And if CS square is equal to 1, it will resist on any scales inside the Hubble radius, and the perturbations will never grow. If you decrease CS square, it means that you decrease the pressure perturbations in the fluid, and below some scale, pressure will resist to gravitational compression, but between this scale and the Hubble radius, there will be gravitational clustering. This is called the Jeans instability. So if CS square is 1 or order 1, there is no such instability. The perturbations are negligible. And then dark energy can be probed with CMB and PK only because it contributes to the angular diameter distance, to the distance to the up to decoupling. So if you changed W, for instance, you change the duration of the lambda-dominated stage. When you integrate from us to decoupling in order to find the angular diameter distance, you find a different result, and the peaks can be shifted. So position of the peaks. Moreover, you affect the late integrated Sachs-Wolf effect. But these two things are not very convenient. The late integrated Sachs-Wolf effect is partially masked by cosmic variance. And modification of the angular diameter distance are anyway degenerate with modification of omega of dark energy today, of the effect of curvature if there is spatial curvature. So you can get some constraints in your parameter space, but you cannot measure independently omega of dark energy, W of dark energy, its time derivative. No way, because you have access to only one integrated quantity. In the matter power spectrum, modifications of the background of dark energy will affect the global amplitude. But as we say, this is extremely difficult to see. It will also affect the evolution of P of eta k, or say Z of k. I can use as a measure of time redshift, at small z, at small z. At small z, of course, if we change the energy of dark energy as a function of time, we change the way in which the growth rate is reduced. This last item is the only way to make a good non-degenerate measurement of the background behavior of dark energy. So this is the right direction to go. And as Shirley will tell you, this can be done in the future with, for instance, LSST or Euclid. If C of S is very small, then in this case, you get some sizable dark energy perturbations thanks to the Jeans instability. And then it changes significance. And then it will change in a noticeable way, especially the matter power spectrum today, because it will get three contributions from baryon, from CDM, and from dark energy. Because really, what we probe is the total matter power spectrum today, without making difference between non-relativistic or dark energy or anything, the total one. So then we would have to include delta rho dark energy in the matter power spectrum, and we could see it directly. But at the moment, people tried to get constraint on this sound speed with current CMB and power spectrum data and found that we have no information at all. Maybe in 10 years from now, we can measure CS of square if it is equal to 10 to the minus 2. But you see, this is a very strong assumption. Okay. I don't have more to say on dark energy. We have 5 minutes. Okay, we started 5 minutes late. We have 10 minutes. Okay. If you are not too tired, so I've been asked to say a word on polarization, a word on tensor anisotropies. It can go really, really quickly. I will be completely qualitative. And it was already in your in the set of notes that was distributed at the end of the CMB chapter. Polarization. Okay, our previous approach for the CMB did not take into account polarization. It was oversimplified, if you want. We said that the photons can be fully described by their temperature. In fact, if you account for polarization, there are more degrees of freedom. In a gas of photons, there are different variables that you should follow, called the Stokes parameter, which refer to both temperature and different types of polarization of the photons, linear, circular, etc. We wrote the Thomson scattering term in our equation for the evolution of temperature. This was a simplified Thomson scattering term, integrated over different variables. And because it was integrated, we didn't see the dependence on polarization. But the Thomson scattering term, when you write it in its first form, depends on the polarization. The photons cannot develop polarization before decoupling. In the tight coupling regime, suppose that you are in a frame moving with a photon baryon fluid. Because it's a perfect fluid, everything is isotropic. You cannot develop polarization at this stage. Polarization is associated to a direction, at least linear polarization. If you had a net polarization in your fluid, it would break isotropy. It's forbidden by the strong interaction in the tightly coupled regime. So polarization can appear when photons decouple. And this is due to Thomson scattering. If Thomson scattering, I put here an electron. Suppose that I have some radiation arriving from all directions on these electrons. If the radiation is isotropic, which is the case in a tightly coupled fluid, the outgoing radiation will be unpolarized. If my electrons now sees an anisotropic flux with, for instance, here I draw a quadrupolar structure because this is what matters. Suppose that the electron see an anisotropic radiation around them. In this distribution, there is a quadruple component corresponding to more photons arriving from one direction and less from the orthogonal direction. The result of the Thomson scattering on the electron will be to create some net polarization, linear polarization in this case. So polarization of the CMB is formed at the last moment just before decoupling. So we can map temperature anisotropies, but we can also map temperature polarization. And in each direction, we can measure the linear polarization vector. So you cannot represent it by colors, but by little sticks. And if you look at the WMAP papers, you will find such maps. So in each point, you have an information about the direction of the polarization and its intensity, which is represented with the length of the stick. It's more convenient to deal with a scalar quantity like temperature. So usually this map is decomposed in something like an electric and magnetic mode. And for each of the modes, since it's a vector field, you can do this, of course. It's a curl and the divergence component. For each of the modes, then you get a map like the temperature map. So for scalar perturbation, you end up with a map of TT, with a spectrum of TT, the autocorrelation of temperature. Okay? This is a spectrum that we discussed before. You obtain it by taking the correlation function of temperature. You get a map for the EE mode, meaning you can compute the two-point correlation function in this map. In principle, you could measure CLBB, but when you study the way in which polarization forms, you see that this term is exactly 0 if you have only scalar perturbations. And finally, you can compute cross-correlation power spectra. For instance, you can build CLTE by taking the two-point correlation function between each point in this map and each other point in this map. And why is it interesting? It's because polarization is generated by the quadrupole of temperature, as we see here. You need a temperature quadrupole in order to get polarization. So the E map is not independent from the T1. The polarization pattern in a given point depends on one component of the temperature and isotropy in this point. This is why there is a net correlation. And why is it interesting to measure this? Well, first, you can follow all the equations that we followed for temperature. You will get, you remember for temperature, we had a source function with the Sachs-Wolf effect, the Doppler effect, the integrated Sachs-Wolf effect. For polarization, you will get another source function related to the quadrupole. So you are probing different combinations of the transfer function on the decoupling map. Instead of being monopole plus gravitational potential plus velocity of the baryons, it is quadrupole of the temperature. It is something else. So you get some independent information. And in the cross-correlation, you cross-correlate this quadrupole with the Sachs-Wolf. And again, you get something different. And moreover, polarization is very useful because the effect of rayonization on polarization is intrinsically different. For temperature, we said that when the universe rayonizes, the rescattering of a small fraction of the photons at small redshifts smears out the perturbation. There is a loss of coherence because the photon you see comes from a direction on the CMB that you cannot guess. So there is a randomization effect. And we said this suppresses fluctuations below a scale corresponding to the Hubble scale at star formation. The patterns for the spectrum for E-polarization in the CMB would look like this in absence of rayonization. In this region, it is a bit similar to the temperature spectrum, except that you don't have the early integrated Sachs-Wolf effect enhancing this. But you see essentially the same acoustic oscillation on roughly the same scales. And indeed, we know that this is generated by theta 0 plus psi, essentially, and this is generated by theta 2, but qualitatively the spectra are the same. In this region, the polarization spectrum goes to 0 because it's like for the Doppler effect. We said here we get anisotropies coming from theta 0 plus Doppler anisotropy coming from the velocity of the fluid, which is like the time derivative. It goes like theta 1. And outside the Hubble radius, there are no time derivatives, so the Doppler effect goes to 0. Theta 2 is like the time derivative of theta 1. So it is also suppressed outside the Hubble radius at decoupling. So this spectrum goes to 0. And this is why it offers an opportunity to learn about rayonization. Because at rayonization, the photons are rescattered, and there is some randomization effect. But the photons are rescattered when they are completely decoupled. And so this last interaction of the photon with the electrons in the intergalactic medium take place with some quadrupole around, okay? Because the photons hitting the electrons are decoupled, so they have a quadrupole component. So there is some new polarization generated. We would never see it if we had a Sachs-Wolf plateau. It would be masked. But because this is going to 0, we can see this new generated component, and it has the same shape as this one, but shifted because the maximum is now set by the Hubble radius, not at decoupling, but at star formation. So it is shifted in amplitude and in position to something like this. And this contribution of rayonization emerges from the one from decoupling. The effect of rayonization is very difficult to see on temperature because if I change the amplitude of my spectrum, the two curves became the same, except that I get an excess in the case with rayonization. This cannot be seen because it is an effect smaller than cosmic variance. This instead is an effect much bigger because cosmic variance on this scale introduces like a 50% uncertainty at most, while here you have a factor 100 typically. So rayonization with current WMAP data is poorly measured, but enough to get the best constraints we have now on rayonization. And clearly I don't have time for tensors, so I will stop here. Thank you. Okay, you might have some questions. Otherwise, I should say that I will leave to take my plane after the coffee break. So this coffee break is the last occasion if you still have some questions to ask. But we can take a few questions now, of course. Well, there were many questions during the... Yes, oh, yes.
Yes. Could you draw the CBBL on that same plot?
The CBBL, yes. So you are really kind. You give me an occasion to say a word about tensors. Okay. Okay. Scalar modes cannot generate this. So tensor modes are generated. We mentioned tensor perturbations. They are generated during inflation just because it's a propagating degree of freedom that has quantum fluctuations. The tensor modes generated during inflation are perturbations of the metric, okay, of the tensor part of the metric. This will be communicated to the tensor part of the energy momentum tensor of the photons. In the tight coupling regime, the photons carry neither polarization, neither tensor perturbations because of this diagonal T mu nu imposed by interactions. But at decoupling, a bit like for polarization, the tensor perturbation imprinted in the metric are communicated to the energy momentum of the photons. And this will be an extra source of anisotropies in the CMB. It will contribute to temperature anisotropy and to polarization anisotropy, both in the EE and BB component. Now, for geometrical reasons, nothing forbids tensor to generate a CLBB. So on the same plot, to answer the question, I can add the spectrum from BB. I love blackboards. And it is qualitatively the same as for polarization, but it has a smaller amplitude. But the amplitude now is unknown. It is completely unknown. It depends on the amount of tensor perturbation generated at inflation. And here we have a free parameter, which is the energy scale of inflation. So this could vary by 10 orders of magnitude. But many models of inflation suggest that it could take place at the gut scale. However, it's only an assumption. It could take place at lower scale, in which case this should be marginally detectable by Planck and the next generation of polarization CMB experiment. It's the same, except that the peaks here correspond to the sound horizon. For tensor perturbation, they correspond to the Hubble horizon. So instead of being set by CS, they are set by the speed of light. So the peaks, the oscillations are out of phase. Okay, so experiments like Planck try to see this B mode, BB spectrum. So far, with WMAP, we only have an upper bound. And the problem is that if this B mode amplitude is too small, we will never see it. First, because our CMB experiment won't have enough sensitivity. And second, because it will be masked by secondary anisotropies, which are anisotropies which adds up at small redshift. And in particular, I didn't talk at all of lensing effects of the CMB. There are some small lensing effects. These lensing effects do generate a BB contribution. And if the tensor perturbation from inflation are smaller than this lensing contamination, we can never see them. So then we could still try to probe these gravitational waves from inflation with the next generation of gravitational wave interferometers, but it will be very hard. Okay, thank you for giving me the occasion.
Thank you. I just thought.
Yes. Yes.
Just a quick follow-up on that. What is this high scale of inflation that it can be seen beyond these tests?
Yes, yes. Okay, I don't know by heart the exact number, but so the best constraint we have on the energy of inflation is from the fact that so far we have not seen this BB mode, and we have not seen the tensor contribution either in the TT temperature, because there would be a contribution here. And so we have an upper limit, but this will be discussed, I think, by Senatore, which is V of inflation at the time when scales cross the Hubble radius, smaller than something between 10 to the 15 and 10 to the 16 GeV to the fourth. Okay? The problem is that what we measure with the data is related to a power to the 4. So we would need an experiment that would be 10,000 times more sensitive in order to gain 1 power in this energy scale. And this will not take place. I think in the future we can gain a factor 100 on this. And so it's like a square root of 10 on this. Okay, thank you. And so I forgot to say, but in the last page of the notes, I wrote a bibliography.
There you said, what have